Hello and welcome back. So we will continue this time our discussion about SVD and how to make it faster. Towards the end of last time, we said that one way to make it faster would be to use the power of randomization. So what I'm going to do now is at a very high level quickly recap where we are right now in our journey towards making SVD faster, and then we will talk about how randomization as a tool can help making SVD faster, right? So what is SVD? So you have a matrix A, let's say this is an M cross T, and then we want to write this as U sigma V transpose. U is an M cross M matrix, sigma is an M cross T, diagonal matrix, and V is D cross D matrix. Last time we saw that one way to make this faster would be to get some orthonormal basis for the span of the top k singular vectors. That is, if U is U1, U2, till Um, but then we care about only the top k rank k approximation for A, then what we really want is rank k approximation would be, let me call this UK sigma k V transpose k, right. So we only need the top k left singular vectors, which is U1 to UK. So we want U1 to UK, and if we have that, then we saw how we can use those vectors to make SVD faster. Just to remind ourselves, what we did was we created this matrix Q, which had just exactly that, the top k left singular vectors of U of A, which is this. And what we did first was project all our columns of A onto the subspace spanned by Q, and essentially what we did was we created this matrix B, which was Q transpose A, and then we did the SVD for B. So B itself can be written as some U tilde sigma tilde V tilde transpose, and then what we observed is if Q was indeed the top k singular vectors, then U tilde would just be an identity matrix, which means that we can pull back the original U by multiplying it with Q itself, right. So which means that we can get an approximation as once we have done this, we would set the approximate Q, which is U hat, let's say, as Q times U tilde, and sigma hat as just sigma tilde, and V hat as just V tilde, and what we will get is an approximation A hat for A, which is just U hat sigma hat V hat transpose. So what we said by doing this is we got something like this. Essentially what we are doing is that we are doing it in two steps, and the reason why we are doing it in two steps is if this matrix is a smaller matrix than the original A, complexity wise we said the original A, if you had done SVD naively, it would take MD squared, but if I do SVD for this guy, so this matrix, so these are all this, so Q itself is like an M cross K matrix. So Q transpose A would just be K cross M into M cross D. So that's a K cross D matrix, but K is much smaller than both M and D. So the dominant, the time complexity of doing this SVD is going to be something like so this is K cross D, so this is going to be dk squared, as opposed to here where this is md squared, where m and d are large, so that is prohibitively large. So this SVD is still okay, dk squared is still okay, we do not have the d squared dependency, so that is good. So that was the advantage of doing this method. So we also said that essentially what we have done is we had the original A, but then what we are approximating A as, using this whole technique of going to B and then doing the SVD, and then lifting it back by pre-multiplying by q is like saying that we are approximating A by q transpose A, right. So that's essentially what we have done. Q transpose A is our B, and we obtained the SVD from that, and then we pre-multiplied it by q. So essentially what we have done is we have projected the columns of A onto the subspace spanned by q, where q is just the top k left singular vectors of A, right. So and this allowed us to think about what we really want, right. So do we really need q, because q being u1 to uk, because we are not going to get that. So at the end of last time we kind of said that, well, we will not really have access to u1 to uk, but that's okay as long as we have some set of vectors whose span contains u1 to uk, we are still okay. Now we finished last time with the question as to how can we get such a set of vectors, such an orthonormal basis for a subspace which contains what we really need, which is u1 to uk. So that's where we stopped last time, and I mentioned last time that that's where randomization as a tool would come into picture. And what we are going to do today is actually get into the details of randomized SVD, right. So what we are going to do today is look at randomized SVD. Okay, so what are we going to do? So the idea is pretty simple. So what we are going to do is, like how in the JLMA or in locality sensitive hashing, we saw the power of Gaussian random vectors and multiplying by it and projecting using it. So we are going to use a similar idea here, right. So what we are going to do is, we have A which is, let's say, A1, A2 till AM. AD. So there are D such vectors in M dimension. Now I somehow want to preserve the column space or the span of the left singular vectors. So what I am going to do is, first let me try to understand what happens when I multiply A with a Gaussian vector, right. So let's say I have a omega which is standard Gaussian with 0 vector 0 mean, means vector of zeros, and identity covariance matrix, right. So let's say I have a omega like this. Now which means that essentially you have omega 1, omega 2 till omega d, where each of this is Gaussian with 0 mean and variance 1. Now let's look at this vector A omega. What is A omega? So A omega is basically linearly combining the columns of A using the Gaussian random variables, which is sum over I equals 1 to t omega I ai. So where is this going to be? This is also going to be a vector in M dimension. So this is M cross D, right. So we have D vectors in M dimension, and what we are doing is essentially taking a random linear combination of these M vectors. Now it's going to be a random variable because omega is random, and now I can ask what is the expected value of A omega. So what is the expected value of A omega? So A is just a linear operator. So this can be written as A into expected value of omega. Because A is linear, expectation is a linear operator, so I can bring A outside. But what is the expected value of omega? It is, by design it is 0. So this is just going to be the 0 vector. So on an average, we are going to see 0 vectors. But what we want to know is, do we have information about the general directions in which A is spread, right? So that's the question that's what we are trying to preserve in some sense, and the question is, do we have that information if I multiply A with omega? So for that we can look at the covariance of A omega, and because it's zero mean, so this is just expected value of A omega into A omega transpose, and that is just expected value of A omega omega transpose A transpose. Again, because of linearity, I can pull these guys out. So this is just going to be expected value of omega omega transpose A transpose. This is nothing but the covariance matrix of omega itself, which is identity. So this is I, because that's how we are generating omega. So this is just A transpose. So this random variable itself, what we observe is that this is basically mean 0 covariance A transpose. Of course, it's also going to be Gaussian, because basically you're doing linear combinations of Gaussians. So this will also be Gaussian. But the interesting thing is that if I just take a linear combination of all the vectors in A using Gaussian random values, now what I get is a vector which has information about the directions of spread of A itself. How does it have the information? Well, it's because its covariance is A transpose, right? So A transpose is kind of telling me is the covariance matrix of A, or the correlation matrix of A, which tells me that in which directions A has information or spread. So what we have essentially done is, by taking this linear combination and getting one vector, we are saying that one vector in general is more likely, in some sense, going to be spread along the direction where A has a lot of energy. When I say energy, it means that if a lot of variance of A is captured in a specific direction, then if I do a random linear combination, then I'm also going to get something in that direction, right? So think of this as you have a bunch of I mean, maybe even in 2 dimensions should be okay. Let's say your columns of A were all like this, right? Right, so these were, these are all the points that correspond to the columns of A and the vectors, corresponding vectors. So which means that predominantly the direction in which A's columns are distributed is this, which means that if I am going to take a linear combination of these using a Gaussian random variable, what I am saying is that, so that is also going to be somewhere along this direction, which means that that random combination has information about where the columns of A generally are spread across. So using this intuition, what we are going to do is the following, right? So we are going to create a random matrix, right? So instead of doing it once, we are going to do it multiple times, right? So because the expectation is 0, and then it's the covariance which has the spread itself, which means that I cannot just do it once, I might have to do it multiple times. So what I'm going to do is, I can think of this as omega 1, omega 2, ... Let's say I do it some L times. We'll worry about how many times we should do it a little later. Now what I'm going to do then is, what is this, where omega rather each Wi is Gaussian with 0 mean and identity covariance. So this is the random part of it, right? So now what I'm doing is, I have D vectors in M dimension, and D is much larger, right? So think of D as 1 million, and M is also tens of thousands. So I have or even 10 million, right? So just to be concrete, 10 million vectors, 10 million dimensional vectors, and then I have 1 million of them. So doing SVD is going to be prohibitively large because it's going to take 10 million times 1 million square amount of time, right? So in amount of operations and hence amount of time taken to do naive SVD, MD squared. So I don't want to do that. So what I'm doing is I'm basically randomly combining the all the 1 million vectors using Gaussian random variables, and then I'm doing this only L times, right? So where L, for now, think of L as much smaller than M or D, right? So because all I want to do is somehow capture the top k as a span of the top k singular left singular values of A, right? So the real place where all of these guys are the real subspace where most of the energy of A is distributed in, right? So that's what I care about. So now what then I will do is I will set L, we'll worry about, think for now L as something like K, right? So if I only want to capture the top K dimensional subspace, I'll think of L roughly as K at this point, which is much smaller than M or D. Maybe K is like 100, right? So maybe there's only a 100 dimensional subspace where all the most of the information of A is present. So I only set L as a small value. Now what I do is I compute this let's say matrix Y, which is A times omega, right? So this is let's call this step 1. So what is this essentially doing? So it is taking the columns of A and then randomly linearly combining using the columns of omega. So basically what I am getting is A omega 1, A omega 2 till A omega L, right? So these are all columns of Y, right? So Y itself looks like this. What I know is each of A omega 1 till A omega L are going to be Gaussian with 0 mean and covariance A transpose. That is, it is kind of capturing the directions where the energy of A is predominantly present. Now, no, in some sense what we are saying is that this is sometimes called as a sketch. This is sometimes called as a sketch of A. That is, I don't know the entire, I don't need the entire A to do SVD, but what I am doing is I am kind of picking some representative linear combinations of A, which is somehow enough for me. Now, well, this is going to be distributed in the directions, hopefully in the directions where the energy of A is spread. Now, what I am going to do next is, as step 2 is find a basis, orthonormal basis for these vectors, right? So I have a bunch of vectors. Now imagine that in the ideal case, all of the columns of A were in some subspace, some k dimensional subspace. Now, which means that if I do a linear combination of those columns, where are they going to be, right? So they cannot go beyond the k dimensional subspace. They are also going to be in the k dimensional subspace. If you want to look at it graphically, think of it this way. So I have, let's say, all of A is in this subspace, which means that let's say this is A1, this is A2, A3, AM, AD, right. So, all the A is in this subspace, the 2-dimensional subspace in the 3-dimensional space. Now, I am doing linear combinations of these, which means that I am combining some W1, I mean some Gaussian value, Gaussian random variable times A1 plus Gaussian random variable times A2 plus dot 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 some Gaussian random variable times AD. So, that might be somewhere here. I am doing this L times, so I might get L different vectors. Now, what I want to do is, in the ideal case, because all the information is in this 2-dimensional subspace of the 3-dimensional subspace, if I had to speed up SVD, I want a basis for this 2-dimensional subspace. Now, what I am saying is, I have taken some linear combinations. I mean, there might be million vectors A, right? So, I mean, these might be so many vectors, right? So, I mean, this might be a million, D might be million, right? So, this might be million, but I don't need those many, right? So, I am just taking linear combinations and then I land up in the same subspace. How many would I need, right? So, in fact, I just need 2 in this case, because the data is exactly in a 2-dimensional subspace. I don't even need 3 linear combinations. I just need 2 linear combinations and then I will get 2 vectors. Now, what I should do is, I need to find an orthonormal basis for this subspace. Why do I need that? Because that's how we started, right? So, we said that if I have an orthonormal basis, then I can speed up SVD itself. That basis is Q, right? So, earlier we said that basis were the exact left singular vectors, but then we said that anything that spans any orthonormal basis of the span of the left singular vectors is okay. So, which means that we need to find such a basis, right. So, now how can we find such a basis? Well, given a set of vectors, I need to find an orthonormal basis to explain this set of vectors. The simplest way to do is, if you have done a basic linear algebra course, you could do something like a Gram-Schmidt's. Right. So, you can do this process of picking one vector, fixing that, and then you can repeatedly try to look at the remove that component from all the vectors and then pick another vector and from the residue, right. So, then you can keep doing this. So, in some sense this is also called as the QR decomposition. Essentially says that if I give you a bunch of vectors, then I can find a set of an orthonormal basis for this vector, right. So, the orthonormal basis are the columns of Q and the linear combination of this orthonormal basis, which gives me each of these columns that I am trying to, vectors that I am trying to explain are in R, right. So, what then I will do is, first I will get these random linear combinations of columns of A, and then what I will do is I will basically do an orthonormalization of this matrix, right. So, and then I am going to call that as Q, right. So, the notation that I am using is Q equals orth of Y, which means that I am taking the columns of Y and then finding an orthonormal basis for this. Now, if the true data, the columns of A were indeed in a top K, indeed in a K-dimensional subspace, then all I need is exactly L equals K, right. So, I just need L or K random linear combinations, they are all going to be in the same subspace, and then I can orthonormalize and then I can get Q, which is what I exactly want, right. So, once I get Q, then I know what to do now, right. So, then the steps are exactly the same. Once I get Q, what should be the next step? Well, I now have to, I cannot deal with the original matrix A, I will deal with projecting the vectors, the columns of A onto the, subspace of Q, which I will do it in 2 steps. I will first do this, this we have seen already. So, I will do B equals Q transpose A, and once I have done that, so the next step would be do SVD of B, right. So, SVD of B, which is write B as U tilde, sigma tilde, we had tilde. And step 5, step 5 of course is, I need to pull back U tilde to the original U, which means that I will set U hat as Q times U tilde and sigma hat as sigma tilde, of course up to the kth position, then that is all we care about, and V hat as V tilde, right. So, and once I do this, then my approximation itself is A hat is just U hat sigma hat V hat transpose. It's exactly the same as like what we did last time, right. So, so the algorithm is, we have almost seen the algorithm last time itself. The only thing that we did not see is how do I get an orthonormal basis, and now what we are saying is, what we are suggesting as an algorithm right now is, do it as follows, right. So, take the columns of A, randomly combine them using Gaussian values to get A omega 1 till A omega L, now, and then orthonormalize these columns, which means that find an orthonormal basis for these columns that you have, and that orthonormal basis will exactly be the basis that we want if the data was exactly on a k dimensional subspace, which is good because then it may not be, Q may not have, the columns of Q may, let me make this clear, the columns of Q may not be U1 till UK, that is not what we are saying, right. So, it can be, it is some orthonormal basis, right. So, U1 to UK may be a special basis for these vectors, right. So, maybe this was U1 to U, so U1 U2, right. So, maybe this was the actual basis. If I did SVD of A, maybe this is the basis that I would get. But what we are saying is that I am picking some basis for these red vectors, which is orthonormal, right. So, that orthonormal basis may be some basis like this, right. So, I mean the length should be 1, so that is true, right. So, this will also be perpendicular to each other. It need not be U1 and U2, but we do not really care because what we really want is, as long as this orthonormal basis, the span of this is exactly the same as the span of what U would give us, we are happy, right. So, what is the span of U1 to UK is going to give us? So, that is just the top k singular vectors, left singular vectors, right. So, if the data itself is in a k dimensional subspace, that is basically the span of the entire data itself. Otherwise, it is just the span of the data projected onto the top k singular vectors. Now, because this, I mean now this is where the Gaussian thing helps, right. So, the Gaussian thing makes sure that the vectors that you are getting have energy in the directions of the top k. Well, if the data itself is in a k dimensional subspace, then it does not matter if it is Gaussian or not. I can take any linear combination and I will still have a bunch of vectors which are same in the same space, and I can orthonormalize that and get a basis which is exactly the same as the basis of the top k singular vectors. But the usefulness of the Gaussian comes into play when the data is not exactly in a top k, in a k dimensional subspace, right. So, there is this error component, that is, if you we have seen this last time as well, if you plot the singular values, right. So, k versus sigma k of A, it kind of goes down and then it does not become 0, but it becomes smaller, right. So, so maybe let me call this T versus sigma T of A, it reduces till k, there is energy till the kth singular vector, and then it becomes, it does not become 0, but there is still this error. Now, in this case, we cannot do random, I mean any linear combination is not going to work, right. So, we need a more principled way of doing this linear combinations, so that the vectors that we get, if we orthonormalize them, we still are approximating the the basis that we would get had we used the top k singular vectors. And for that, the Gaussian helps, because every time I do a random linear combination, I know that the Gaussian has the information in terms of the covariance matrix, right. So, the covariance, I mean, basically it is capturing the directions of high spread, which is basically the top k singular vector directions. That's why you need to use the Gaussians, right. So, we'll talk about this a little bit more detail as we go along, but let's quickly see first of all the computational complexity, right. So, in all this, the whole goal was to make sure that we can do this faster, but let's just make sure that we are doing this faster, right. So, let's go step by step. So, the first thing I had to do, let me use a different color here. Yeah, the first thing I had to do was to generate this omega. What is omega? Omega is I have so A itself is m cross d, and then omega is A is m cross d, and omega should be d cross L, right. So, that is my omega, so that I can do A omega. So, to generate that, is going to take order of dl time. So, because I need to generate d into L numbers, right. So, each of these is Gaussian. So, let us say one operation per Gaussian entry. So, that is going to take order of dl. So, now I do A times omega. A is m cross d, this is d cross L. So, when I do this matrix multiplication of an m cross d matrix with a d cross L matrix, so that is going to take order of m d L, right. So, that is the matrix multiplication time taken. So, this is we'll finally aggregate all these boxes and see what is the effective time complexity. Now, I need to do Gram-Smith or QR decomposition. Well, this is as costly as a kind of doing an SVD, but the thing is that Y is now an m cross L matrix, right. So, it is not an m cross d matrix. So, the time taken for doing this orthonormalization is just of this is m cross L. L is much smaller than d. So, this is going to take order of ml squared, right. So, this is the time complexity for step 2. And then what we do is we are multiplying again Q transpose, which is L cross M times M cross D. Well, that's a matrix multiplication, that's still going to take L into M into D, which is same as MLD that we saw earlier. This step is still MLD. Now, I am going to do an SVD of B, but B is a small matrix, right. So, B is L cross D, that is the whole point. We do not want to do the SVD of original M cross D, we are doing it for L cross D, where L is much smaller than D, and we know how much time this takes. So, this takes order of dl squared, right. So, that is I mean, when it was M cross D, M was larger than D, so it took MD squared, but now because we have reduced M to L, we only have L vectors, and then if we do it for a D cross L matrix where L is smaller than D, the smaller will square. So, this will be D times L square, right. So, that is the time taken for the SVD itself. And then we will again do we will take the top k of this guy and set u hat as q u hat. So, that is going to take another m Q itself was dl, sorry, Q was ml, and this is lk. So, this is going to take order of mlk. So, if I put together total time complexity, let us look at this. So, that is order of dl to generate omega plus, so this, let me note down what this is to generate omega plus order of MDL. MDL is needed to generate y equals a omega plus order of DL squared. So this is needed for orthonormalizing y, and then we want to do Q transpose A. So that takes MDL, the same thing as before. So this is for Q transpose A, and then we have order of DL squared for the actual SVD, which is what we are trying to save anyway, right? So this was SVD of B, this is B equals Q transpose A, and finally to do this pullback, we need something like order of MLK. Remember, K and D are K and L are similar, so you can think of this as order of ML squared also. So this is the pullback part, pullback U. So now if you look at the the dominating terms here, so DL, of course this MDL, there is an extra M, so this is going to dominate than the DL, so I don't have to worry about this. Now of course M is much larger than L, so DL squared is also going to be smaller than MDL. So this is MDL, so this is going to be smaller. Well, K is also smaller than D, so this is also going to be smaller than MDL. So the whole thing is going to be order of MDL, right? So where L, you can think of L roughly as like K for now, right? So that's the number of random Gaussian linear combinations that I'm actually computing. So that is going to be MDL. Now compare this with naive SVD. Remember, naive SVD took MD squared, and that's precisely the gain that we are getting, right? So the D squared, what we have gained is if M is in million, D is in another million, but L is just 100. Now we have reduced the the computational complexity by a factor of D, and because you can treat L roughly as a constant, right? So and that's a huge saving in practice, right? So the whole discussion of this course is to save, run things faster at scale. And at no point in this whole discussion have we done an SVD of a M cross D matrix, right? So it's always about the smaller matrices, the sketches and things like that. So that's where the saving comes from, right?